Hi, today we're going to talk about a new approach for quantitative risk analysis, QRA. The new approach is called Most Probable Severe Case. Accident prevention and their consequences in the chemical and process industry has been a major task for the last decades. The first step to prevent the damage is to assess the strength of the accident event and decide what are the measures to prevent the accident event and or reduce the damage arise from the accident. In a world with limited resources, the ability to decide what would be the best way to invest in order to prevent or protect the risk is a crucial decision. There are many methodologies proposed for the risk assessment in the chemical process industry. The most notable ones are the quantitative risk analysis, which we call the QRA, and the worst case risk analysis. We will talk a little bit about the QRA. The main step for the method are hazard, which is the hazard identification. It could be done by hazard studies, which is hazard and operability. Could be done by FMEA, which is a failure mode and effect analysis, what if analysis, checklists, and many other kind of hazard identifications. There is no distinguish between strength of events nor the likelihood. All scenarios are accounted for this QRA. The likelihood occurrence done by fault tree analysis, event tree analysis, or using process and failure probabilities data from different sources. After collecting all the data, a physical effect calculations using mathematical models is done in order to predict the vapor's cloud dispersion, toxic release, fire, explosions, etc. The QRA combines physical effects with likelihood and environmental conditions probability to get the individual risk curve or the social risk curve, which means the probability for one death per year. This method accounts many different scenarios, small like big ones, with different probabilities, while each scenario adds to the result by its weight, the strength of the effect multiplied by its likelihood. Even the negligible and the smallest event is accounted. These results do not contribute to the emergency planning where deterministic results are needed. The other type of risk evaluation relies on the most severe or most worst case scenarios. This method uses similar steps as QRA, such as hazard, and then physical effects calculations, but accounts the most severe effects regardless its likelihood. Such an assessment results with overprotective requirements, which could be expensive and unnecessary in most cases. This is the reason that we introduce you now a new approach. This approach is the most probable severe case, which combines the best of these both methodologies. This method is very efficient and accounts only few different scenarios with significant probabilities and physical effects. Judgeable events are not accounted. The method steps is, again, we start with hazard using a hazard study or FMEA, what-if analysis or checklist. Likelihood of occurrence using fault tree analysis, event tree study, or data from external sources. But we need to remember that negligible effects are not accounted. The third step is choosing the most significant event with likelihood of more than 10 power minus 6 per year. For different effects such as fire, explosion, toxic dispersion, each one of these effects will have its own scenario. The physical effects calculation will be using mathematical models in order to predict the vapor cloud dispersion, toxic release, fire, explosion, etc. We will show a simple example of ethylene pipeline, diameter of 60 millimeters with length of 300 meters. The possible event of a pipeline is a leak. It could be a small leak, which is a diameter less than 10 millimeters, usually 1 millimeter. It could be a medium leak, which is exactly 10 millimeters, or a full bore, which will hold the entire 60 millimeters of the pipe diameter. The consequences of such leaks could be fire, if the leak will be ignited immediately when it escapes the pipe. It could be an explosion, if the ignition will happen after few seconds, or it could be a toxic dispersion if the leak would not be ignited at all. Now we'll find the probability of the events. We take the scenario of a small leak. We know that the probability of this small leak is 10 power minus 4 per year. We got this data from the CPR 18E, which is the TNO purple book. The events could be ignition, delayed ignition, which could cause explosion, or dispersion, where there is no ignition at all. The ignition would take 1% of the events, and it will result in fire in the probability of 10 power minus 6 per year. Delayed ignition or explosion will not take place when we're talking about small leak. A dispersion of toxic gas would take 99% of the events, so its probability would be 9 times 10 power minus 6 per year, which is a high probability. Now we go to the medium leak, which is 10 millimeter diameter. This probability is 5 times 10 power minus 5 per year. The ignition event would take 10 times 10% of the leaks. Delayed ignition, which could cause explosion, would take 5% of the leaks. And dispersion without any ignition would take 85% of the leaks. So the end event, which is fire, will be 5 times 10 power minus 6 per year. Vapor cloud would be 4.25 times 10 power minus 6 per year, and the explosion will be less than 10 power minus 6 per year, so we will not count it. For the full bore scenario, actually the full bore itself starts with a probability of 10 power minus 6 per year, so all the ignitions, explosion and dispersion would be less than 10 power minus 6 per year, so we will not account any of this. After we collected all the data, we make a circle of all the events, the end events, which have probability of more than 10 power minus 6 per year, and outside the circle all the events which have probability of less than 10 power minus 6 per year. For the full bore, we saw that all events are negligible and would not happen in the probability of more than 10 power minus 6 per year. For the medium leak and the small leak, we saw that fire and dispersion would be inside the circle of that probability. If we need to choose between them, the more severe event is the medium leak. That's why these would be the events that we need to calculate in order to see what are the consequences of such a leak. For summary, we see that we need to calculate the effect of the two scenarios from the 10 millimeters leak, which are toxic vapors dispersion and fire. We can also see that explosion effects don't have to be calculated, as well as any effect result of the full bore event. We can see that the most probable severe case method enables to provide an accurate risk assessment in order to design proper protection elements without considering the negligible events, if by probability or by severity, and this makes this method very, very efficient and cost effective. Thank you. For further information, you could meet us at www.ornan.com.